and its launch is scheduled for 2018. In the next decade, we should be getting a much better idea of the constituents of the planets, of the atmospheres of planets around other stars. Again, that we have not seen yet. So, remarkable, all right?
With what instrument did they make this?
One of them was STIS, and the other is WIFC-3. Oh, and there are a number of groups. STIS is actually generally been used for this. And people are doing it from the ground. It's difficult from the ground, but the further you go into the infrared, the less the effect of the atmosphere. And so you're able to get around this difficulty of the uncertainties produced by the Earth's atmosphere. In any event, in the exoplanet community, there is a feeling now that there have been some identifications of molecular species. But you can see it's still at the 3 sigma level. But the fact is, this is an explosive area of research and guaranteed to meet with more success in the next decade. Okay, Hubble. Hubble hasn't done much. I shouldn't say that. It hasn't done much in terms of the study of our own solar system compared to probes, right? In astronomy, you've got to look at radiation. But if you can send a probe there and actually dig a hole and do a chemical analysis, that's the way to go. But still, Hubble has done some things, and I must tell you that the Hubble is responsible for the declassification of Pluto as a planet. And yeah, everyone laughs, and I still get letters from people because, in fact, I had something to do with writing what do we call it? So I blank out on the words, but the IAU, the resolution that we voted upon that changed Pluto from being a planet to a dwarf planet. In fact, it's simply history repeating itself. So here's a diagram of the solar system. Here's a blow-up of the inner solar system. The fact is, for the past century, we've had 9 planets. But it was not always that way. When the first asteroids were discovered, first day of the 19th century, January 1st, 1801, Ceres was discovered. Turns out to have a radius of around 400 kilometers. It's round, it's in hydrostatic equilibrium. Within the next couple of years, 3 other such systems were found, all having similar sizes, Pallas, Juno, and Vesta. They were considered planets. That's before all these other tens of thousands of asteroids, which are much smaller and fainter, were discovered. So initially, and that was before Pluto was discovered, so I can't remember, there were 6 planets or whatever, and then 4 were added to it. So at one time, there were 13 planets. And then when it was realized that Ceres, Juno, Pallas, Vesta were simply the top end of the mass distribution for what we now call the minor planets or asteroids, they were declassified. So those 4 were legitimate planets for some decades. And then when it was realized there was 10,000, 20,000 more like them, they were out. Same thing happened with Pluto. Now, the asteroids are believed to have been a planet or protoplanetary system that didn't quite make it to a planet because of the very strong tidal effect of massive Jupiter, its gravity. So the same thing happened with what are now called the Kuiper Belt objects, which exist out past the orbit of Neptune. And these were discovered by David Jewett and Jane Liu, who received the Shaw Prize for this discovery either 1 or 2 years ago. In fact, it was just last year. Their discovery of, 20 years ago, was that there are other objects out here, like asteroids, although these, which are confined to the plane of the solar system, are more spherically distributed. And the fact is, Michael Brown of Caltech, who has been studying these with the Hubble, some of the brighter ones, demonstrated that one of these objects out there, which is, I can't remember, 3 times further than Pluto. It's further than Pluto, very faint. Here's the best that Hubble can do with it. And the fact is, plotted to the same scale, you have this object out there that is within 5% of the size of Pluto. And there's another object, can't remember the name right now, that are basically this size. So you have the same situation here where Pluto, which was considered unique out there, or isolated, until the discovery of the Kuiper Belt object. Now we realize that there's a myriad of other objects like that. So if Pluto's going to be a planet, they should be a planet. And so this was the question confronting astronomers, whether or not we should increase the number of planets, consider all of the Kuiper Belt objects that were large enough to be in hydrostatic equilibrium to be planets, or whether we should consider this not a planet because, in fact, it formed differently than the other planets. And so by a close vote, the Union of Astronomers decided, no, Pluto should be declassified and it's now considered a dwarf planet. But you can call it whatever you want. Objects in space are not governed by law. Hubble has discovered, just in the past year, other satellites around Pluto. So Hubble has actually made some solar system discoveries. All right, let's move out in space. There are a number of interesting morphologies of objects in space. And what is fascinating about them, in fact, there are 2 of them, I'll tell you. There are jets, that is sort of linear features, and there are arcs, 2-dimensional features. And what is interesting about them is that they occur frequently enough that we believe that anything out there is governed by natural laws, and there must be a reason that those morphologies exist. And they have been a puzzle for many years that recently has been resolved, we believe. So I'm going to start with jets. Jets are these linear features of radiating gas that occur over many orders of magnitude scale. Here are 2 stars in formation. HH stands for Herbig-Haro. So here are some stars in formation, and you see this prominent jet here having a dimension of around 10 to the minus 3 light year. Similar situation here, where you see the evidence of a disk, and this dark feature is produced by a dust that is absorbing the radiation in the disk. Generally, when you see a disk, when you see a jet, there is evidence, for a disk. And you actually see it here also in a, if I can get this. Well, it shows up. That's interesting. Shows up. Let me try this. There we go. You can see a similar thing here in an image taken by Hubble. Generally, at right angles to the jet, which is moving outward, you see evidence for a disk. And here is a group of galaxies in the constellation Hercules, where you see this radiating jet that finally breaks out into these look like dumbbells or barbells, having a size distribution of 10 to the 5th light year. So this is a phenomenon that exists over 8 orders of magnitude. Monstrous, huge thing. 100,000 light years, 1,000th of a light year. So what causes them? The puzzle, well, there's another well-known example, and it is a jet that is emanating out of a nearby massive galaxy, M87. Again, you can see over some thousands of light years this jet is maturing. The puzzle is, and this is polarized and emits synchrotron radiation. So it's really hot, relativistic, and since it involves synchrotron radiation, there must be a magnetic field. Interesting. the puzzle in understanding these features is that you have radiating gas. That means it's hot. That means it has thermal pressure. So why is it confined when the thermal pressure would lead you to believe there should be some opening angle and then it would expand? And the current thinking is that it is due to what has been called the magneto-rotational instability. That was proposed by Steve Baldus and John Hawley, who got the Shaw Prize for this seminal paper this year, actually. A paper in which they show that if you have a disk in which some central object is accreting material from a passing star or an interstellar cloud, and you have a magnetic field generally due to the spinning object in the center, like a star, right? We could have, the sun has a magnetic field. So if it were accreting material, what they showed was that there is an instability that they called the MRI, magneto-rotational instability, that basically causes ionized material, as the accreting material falls down a potential well, it becomes hotter and gets ionized. Charged particles interacting with a rotating, a differentially rotating magnetic field, or disk with a magnetic field in it. And what that does is the differential rotation causes, which is trapped by the ionized material in the disk, which is rotating around, causes a twisting of the magnetic field. And so when you have the accreting gas, which builds up its thermal pressure as it falls down the potential well, what happens is there's some of that material will collapse onto the central object, whether it's a black hole or a compact object, and some of it, from its thermal pressure, will rise up out of the plane of the accretion and be trapped by the rotating magnetic field, which confines itself and actually gives impulse to the gas and sends it out. And so it is believed that this MRI is the cause. Let's see if I can bring up now. Here is a supercomputer calculation done by Chris Fragile and collaborators. Boy, it's so quick, I didn't have time to. What they do is basically take this. They have an accretion disk, and they have these twisted magnetic lines. The green is coming out, the blue is going in the other hemisphere. And basically, they follow the entrapment of gas that is in this pinkish disk to see exactly what results from it. So this is an MHD calculation, and what you see essentially is, after a period of time, when you get sufficient entanglement of the magnetic field, you get these jet fuels. So we believe that the MRI is what causes those jets. Now, the other interesting morphology that one sees is arcs that are produced by gravitational lensing, right? General relativity. Einstein predicted this. It was confirmed by Eddington, measured the angular separation of two stars in the solar eclipse in 1919 and showed that, in fact, that they were changed when the sun was positioned in between them. And it was that experiment that was successful that led to Einstein's Nobel Prize, because he did get the prize for this, basically. But many of Hubble's most spectacular images are of, here's an Einstein ring, a massive galaxy, there's a distant object, and the gravitational lensing takes that image of that galaxy and spreads it around into a ring. And here's another example where you have a system of galaxies, a distant galaxy that you see basically forming an arc. This is all due to gravitational lensing. And there's a little cartoon here that essentially describes the process. You have your distant source, you have your strong gravitational field here, And so what you see basically are an odd number of images, either 3 or 5. Actually, it's usually 5, but the 4th and the 5th are so faint they're usually not detected. So you usually see, you can detect three images. And this is exactly the process that leads to these arcs. What is interesting about this situation, there are two things. Here's a Hubble image of a cluster of galaxies. And you see two objects that are gravitationally lensed. You see a distant quasar here, and here you see the 5 images for this object. Then you also have, not associated with a quasar, 3 images of a distant galaxy. And so this is called strong lensing, gravitational lensing. In fact, any distant object will have its morphology changed if it happens to lie along the same line of sight as a massive cluster. And its shape will be very slightly changed, and that is called weak lensing. You don't get an arc, but the fact is, if you analyze all the images that you see around a massive cluster of galaxies, you can build up a mass distribution of the cluster. And this is what has led to the existence of dark matter and its distribution in space. Because, well, I'm getting ahead of myself. Let me step back for a second and say there are two interesting things, the physics, about this situation. The first is that you can use both the arcs, strong lensing, and the change in morphology, the slight change from, let's say, a point source to something that is oblong because of the gravitational effect here, to map out the mass distribution. Okay, that's interesting. The other interesting thing is that it turns out that surface brightness is conserved in gravitational lensing, and so when you get 3 or 5 images of something, you can study all 5 of them, and the object's intensity is magnified. So you can actually detect distant objects that otherwise would not be observable by using gravitational lensing. And this is, I'll come back to this, depends whether I have time or not. This is going to be the last great, large, deep field program of the Hubble that has just started in the past several months, where there are 6 massive clusters of galaxies that are producing arcs, and I'll show you one. And we are using the gravitational lensing from these 6 clusters to be able to detect very distant galaxies that we would not otherwise be able to see. Not even Hubble could see them, were it not for the fact that they are being gravitationally intensified. And so we're hoping to be able to see with Hubble basically the earliest galaxies, which we wouldn't be able to detect because they're so faint if it weren't for this effect. And almost 1,000 orbits, that's 4 months of Hubble's time will be devoted to this program that has just been undertaken. And at lunch we were just talking about the fact that within the past 48 hours the first cluster has been done, and this morning the first paper was submitted on the results of the data that appeared less than 48 hours ago. Really interesting stuff. In any event, so here are several clusters, and you can see this is one of the richest. It's a rich cluster of galaxies, and look at all of these really interesting arcs here. And of course, there is also weak lensing. So the point is that we take images, deep images of these clusters, and try to map out the mass distribution of those clusters. And what we have found is that there is much more mass there, which is represented by these contours, than the radiating galaxies that we actually see. And this is why this term dark matter has arisen, because you see, so I'm not sure if I've explained that, but you actually see in different colors here the actual images in different wavelengths and different filters of the galaxies in this system. And from the gravitational lensing, we infer the existence of mass that apparently is not radiating, because you see these contours there, meaning there is mass here, but it isn't radiating. And there's enough of it. You could say, well, there's not much mass there, so perhaps it's just not bright enough to be seen. The fact is, the amount of mass that is inferred from the gravitational lensing is an order of magnitude or more greater than the amount of mass that you infer from the brightness of the galaxies that you see. So that's why this paradigm has arisen, that most of the universe consists of matter that does not interact with radiation, whose existence is inferred only from its gravitational potential. So dark matter. And it has been plotted this way. And let me show you another cluster that's even done more accurately by a colleague of mine at the Institute, Dan Coe. Here's one of those other clusters I showed you. You can actually see here the Hubble image, and this grayish whitish fuzz is the distribution of the dark matter that they infer. So, interesting. It is clumped. The dark matter is not spread uniformly through space. It does appear to be clumped, associated with the gravitational potential of normal matter, baryons. And this is what has given rise to the term cold dark matter. If any of you follow cosmology, it is believed that the dark matter is cold, not hot. What does that mean? It means that it is clumped. So if this were neutrinos, that would not be nearly as influenced by the gravity. It would not suffer, let's say, the clumping due to the gravity of the galaxies. So the less the energy, the internal energy of the dark matter, the more likelihood it is to be clumped. And because it is inhomogeneous, the dark matter must be cold, not hot, not really energetic. Okay, finally, deep fields. Just another pretty picture. This is the ultradeep field. This was done after our original deep fields when they put in a better instrument. Lower read noise, larger. So, but the fact is, we undertook early in the life of Hubble, after it was repaired, looking at blank fields just to see what we could see. Had to be done. And this basically is the so-called ultra-deep field. Image of a grain of sand at arm's distance. So it's several square arc minutes, really small area of the sky. And you see a couple of stars here that are foreground stars in our Milky Way, and about 5,000 very distant objects, some of which are brighter and therefore closer than others, but many that are probably very distant. Although some of them may be small and close. That's the interesting thing here. So this is an interesting image, but very difficult to interpret unless you know the distances. And of course, one of the fascinating things about astronomy, sorry physicists, is astronomy is the only discipline that looks directly into the past. Paleontology, archaeology, they're great, but you're looking at artifacts that have to be interpreted. Because of light travel time, we actually see what's happening billions of years ago. And because we're such cool dudes, we can actually see with Hubble back 95% of the time to the Big Bang. I'm going to talk more about this. Look back time, okay? Big Bang occurred 13.7 gigayears ago. And we deal with a term that's redshift that I think at least you've heard about, and it's simply redshift is the wavelength that you observe something. Okay, the universe is expanding, you know about the Doppler effect. So the wavelength you observe something minus its wavelength in the lab divided by the wavelength, that's called the redshift, Z. And it is a unit that we use that basically measures distance. And it is related approximately. This is just for this colloquium because this is a more complicated expression here depending upon the cosmology, and it's got exponents of 2 to 2/3 and things like that. But the point is that we always deal with redshift. And the look back time that you're looking to at no redshift, current epoch, right? So look back time is 0. But when you get to large redshifts, as soon as you start talking about redshift of 10, you're looking back, right, 90% of the time to the Big Bang. So I'm going to use that terminology, thank you. And it is important in understanding the deep fields. Here is a detail of the ultra-deep field. And so this is just some of the sections of what I just showed you. And again, if you want to do a 0th order analysis of this, clearly some of these objects that have larger sizes and are brighter, that must be relatively nearby, they appear to have a symmetry, okay, classic spiral here, like our Milky Way. When you look at the more distant objects, they tend to be smaller, they're bluer, turns out the stars are younger, hotter, and much more dysmorphic. And so my colleagues tend to call these garbage galaxies as opposed to very nice, or train wrecks. Take your pick. But if you really want to understand how these objects are evolving, you got to get their distance because that'll tell you the look back time, right? So universal expansion. So we use the redshift basically to get the distance. It's directly related. Now, from this simple seat of the pants analysis, it looks like, and it turns out to be correct, basically. If you look at the nearby galaxies in the, you see objects like this, very large, amorphous, either this so-called elliptical, we call them elliptical galaxies, or spiral. But when you look at these smaller dysmorphic ones, these are the ones that we're looking at early on. It does look like, to 0th order, the evolution of the universe as manifested by galaxies, which are the largest gravitationally, well, not quite. Clusters of galaxies are actually larger, but galaxies, you start off with these dysmorphic things that formed out of the initial inhomogeneities, quantum fluctuations, and I'll show that in a couple of slides, and ended up like that. So, how did it take place? Well, first of all, and here I am going to skip some things. So let me say that the interpretation of the deep field was made essentially by 3 years of time of spectroscopy of the brightest objects. So this is the original deep field. The University of California, University of Hawaii, and Caltech, which have time on the Keck telescopes in Hawaii, had a program for 3 years in which they took spectra to get the redshift and therefore determine the distance and therefore the look-back time of the brightest 125 objects in the deep field. And it took huge amounts of telescope time. But it was transformational in our understanding of the interpretation of the deep field. Because we can look at these objects now and say, yeah, okay, that is larger, it is closer, its redshift is only 0.2. And then there are some really distant ones here. Where is the one at 4? Redshift of 4. Lower left.
Next to a equal one. The yellow galaxy.
Here we go, thank you. Yeah. Redshift of 4. Ultradeep field actually went fainter. This was transformational. Now, it took a lot of time and effort on telescopes to get these spectra.